Hello and welcome. Last time we started our discussion about revenue loss due to market delays, and we worked out some examples where the lifetime was 52 weeks and delay was 4, and lifetime was 52 weeks and delay was 10. And we got very alarming results. For just a delay of 4, the loss in revenue was about 22%, and for the 10 weeks delay it was 50% revenue loss. So this just signifies how important it is to launch a product at the right point in the market window, which is denoted by this big triangle. So after having discussed that, we can take a look at some of the other design metrics like NRE and unit costs of the system. And basically, what are the costs involved? There are different costs that are involved. So unit cost is the monetary cost of manufacturing each copy of the system, excluding the NRE cost. So once the product is made, the cost to produce one copy of that product is the unit cost. So what is NRE cost? It is the one-time monetary cost of designing the system, which includes the cost for research and development. And what is total cost? Total cost is NRE cost plus unit cost into number of units. And of course we can have another cost is the per product cost, which is the total cost divided by the number of units. So these are the two formulas. For example, for 10 units, total cost is 2000 plus 10 into $100. If $2000 is the NRE cost of the system. So NRE cost plus unit cost into number of units, which is 10. So it comes out to be 3000. And similarly, we can find the per product cost. So amortizing NRE cost over the units results in an additional $200 per unit, right? So what is this? This is the contribution of the NRE cost on the product cost. So that just explains why Intel uses an expensive technology like VLSI, and when it manufactures the microprocessors, it divides this cost over the number of units. Since the number of units is very large, in millions or billions, this per product cost remains low because the contribution of this factor remains low, right? Now we can have NRE cost and unit cost metrics, right? We can this analysis is important because if we want to manufacture an embedded system, we must find out the appropriate technology in which to manufacture an embedded system. Some technologies are cost effective for small number of units like FPGAs. Some technologies are cost effective for the moderate level of units, and some technologies like technology C would be feasible for very large number of units produced. So that can translate to technology A can translate to a PLD, programmable logic device. Technology B can translate to an ASIC, and technology C can translate to VLSI, the most advanced IC technology to manufacture an embedded system. Now, if you want to write the equation for the total cost using technology A, right? What is the formula of the total cost? We just discussed previously. It is basically NRE cost plus unit cost into number of units. Let's say the number of units is N. So for technology A, let's call it total cost of technology A. It would be given by NRE cost plus unit cost is 100 into number of units, which is N. Let's call it equation 1. So what kind of an equation is it? What kind of function does this equation represent? It represents a straight line. Now quickly write the expression for total cost of technology B and technology C using the same thing, right? The total cost of technology B would be 30,000 plus 30N, and for technology C would be 100,000 plus 2N, right? And all these three TA, TB and C are all straight lines. So if you want to plot these three graphs would represent straight lines as I've been shown by this, right? This is the graph for total technology or TA. This is the graph for TB, and this is the graph for TC, right? And these graphs are intersecting at this point, right? So we are basically want to find the point N1, and we want to find the point N2. So what does point N1 represent? Yes, intersection of technology B's graph and technology A graph. Technology A and technology B's intersection, right? So how we can do that? We can equate TA equals to TB and then solve for the value of N. Okay, students, please solve this out and tell me. What about N2? N2 is the intersection point for technology C and technology B. So let's find the values of N1 and N2. So once we have found the values of N1 and N2, like the graph is telling us, when the number of units is less than or equal to N1, the total cost of technology A is less than the total cost of technology B. So what does it signify? So if we want to manufacture small number of units less than or equal to N1 in this region, we would select technology A for the less total cost. On the other hand, what does N2 signify? That if the number of units is greater than or equal to N2, then technology C would be selected, because the total cost of technology C is less than the total cost of technology B. So that is how this important analysis is used for interpretation. So what about the points between N1 and N2? What if our number of units is greater than N1 but less than or equal to N2, which means this region? So which technology should be preferred? Technology B, because in this region the total cost of technology B is less than the cost of technology A and the technology C. So technology B or AC would be selected at this point. Beyond N2, of course, technology C would be feasible, which would be of course VLSI. So that just explains why Intel uses VLSI for manufacturing millions and billions of processors, because at this high volume production VLSI becomes feasible. On the other hand, Intel won't use VLSI for prototyping or testing the microprocessors. So PLDs or FPGAs for that matter is the technology that is most suitable for prototyping or testing your hardware. So but we must also consider time to market, because VLSI would be good, but it would take more time to bring our product to the market. So now let's look at the performance design metric. This is a widely used measure of the system, but it is widely abused. So for us, being users of embedded systems, clock frequency doesn't matter, instructions per second does not matter. So what does matter for us? The function of the embedded system. If the embedded system is faster in carrying out its function, the performance is good. So for the digital camera example, user cares about how fast it processes images, not clock speed or instructions per second. Similar is the example of printers, like I gave before. Pages per minute is the performance criteria of a printer, not the processor, not the amount of memory, and not the hard drive or any device that is in the system. Latency, response time, again would be with response to the task of the system. Camera A and B processes images in 0.25 seconds, right? So we'll measure it by the performance of the application for which the embedded system is designed. Throughput, tasks per second. Let's say camera A processes 4 images per second and camera B may process 8 images per second. So what would be the speed up of camera B's performance as compared to camera A's performance? It would be 8 divided by 4, twice. So when, as far as embedded systems are concerned, there are these technologies that can be used, and technology is given by the manner of accomplishing a task, especially using technical processes, methods or knowledge. So when we want to make an embedded system, there are three key technologies that we have to decide. One is the processor technology that we are going to be using for our embedded system. Second is the IC technology that we would be using for our embedded system. And the third would be the design technology that we would be using for our embedded system. Let's examine these three technologies in detail. First, we'll have a look at the processor technology. What is the processor technology? The architecture of the computation engine used to implement a system's desired functionality. Basically, in this stage, we select the microprocessor technology that we would be using, or the processor technology that we would be using. Either we would be using a general purpose processor, or we would be using an application specific processor, or we would be using a single purpose processor. The main point over here is processor does not have to be programmable. For example, when we look at the single purpose processor or SPP, SPP does not include program memory, or in other words, SPP is not programmable. And also processor does not equal to general purpose processor. In other words, we can say that general purpose processor is an example of a processor technology. Well, there can be others as well. And of course, we can have this application specific processors, which are also called ASIPs, application specific instruction set processors, right? So this is basically equal to some of these details. One of the things we can notice that in the case of the general purpose processor, or any processor for that matter, there are two components basically. One is the controller and the other is the data path. Your controller is your main controlling sequential circuit that controls the processor, and this controller is present in all these three processor technologies. So the processor controls or configures the data path for particular operation. And what is the data path then? Data path includes all of the hardware basically that is present in the processor, like the registers, the arithmetic and logic unit, data memory, etc. So we can say that the controller configures the data path for different kinds of operations. For example, over here we have this example shown that we have move AX, BX, right? So when this instruction executes on the general purpose processor, the data path would be configured such that BX becomes the source register, which is read by the controller, and AX becomes the destination register, which is written by the controller. Similar is the case in this instruction. Over here, AX would be configured as the source and BX would be configured as the destination. One more point that we can note over here, that the arithmetic and logic unit of the general purpose processor would be generic ALU, and this generic ALU would be designed to carry out all mathematical and logical operations, because it's a general purpose processor we are talking about. But in application specific processors, we will have a custom ALU, and this custom ALU would be optimized for certain types of operations that are application specific to the use of this particular application specific processor. One classical example is when we have an application specific processor. An example is the DSP, or the digital signal processors that we have. So digital signal processors have a custom ALU in which the MAC operation, or multiply and accumulate operations, are optimized. So we'll have special functional units or mathematical units to carry out this multiply and accumulate operation very fast. Now, discussing processor technology further, this is an excellent slide that basically telling us what do we mean by different processor technologies and how the different processor technologies map to the functionality that we want from our embedded system. Let's say, for example, this solid plus sign is basically our desired functionality that we want. Now, these three figures are telling us the amount of nearness that our processor technology has towards our desired functionality. We want this, but when we start with a general purpose processor, this is something very broad. So it doesn't actually map really nicely to this desired functionality. So we need to program it in order for it to map into our desired functionality. On the other hand, as we can see that application specific processors seem to be more closer towards our desired functionality as compared to the general purpose processor. It means that application specific processors would need less customization to map to our desired functionality, because they have got some similarity and some functional units that are aimed towards our desired functionality. The best example is again a digital signal processor or a DSP. For example, if this desired functionality was our DSP operation, it might be a finite impulse response filter or anything else. So if you use an application specific processor like a DSP processor, it would be very near to our desired functionality. Let's now turn to the single purpose processor. So what do we see when we see a single purpose processor? Isn't it a strong match or a perfect match for our desired functionality? Yes, it is. And why is that? Because a single purpose processor was designed for this desired functionality. Or in other words, single purpose processor performs only this single purpose function, that is our desired functionality. Our single purpose processor does not do anything else except our desired functionality. So it is highly optimized towards our desired functionality. So if our desired functionality was this loop, so our single purpose processor would only be designed to execute this loop, nothing else. And you can imagine that if we have something very specific like the single purpose processor, how specific it would be in terms of the resources. It would include only the resources that are needed to carry out, for example, this for loop and this plus operations and this particular memory. And one point again that I would like to mention is that single purpose processor won't have program memory, because it is not designed to be programmable. It is a hardware processor or a hardware accelerator for that matter. So afterwards, now we can look at the specific points regarding general purpose processors. They are programmable devices, right? So general purpose processors are programmable, just like the normal microprocessors that we have in our desktops and our laptops, right? Even Raspberry Pi comes under the category of its general purpose processor, for that matter. It is also known as a microprocessor. And what is its feature? It features a program memory, a section of memory where code is stored, code or program stored, has the concept of stored program, and it contains a general data path with large register file and general purpose ALU. Why the register file has to be large? Because it must carry out all different kinds of activities. For example, your general purpose processor, aka microprocessor, should be able to run any operating system. It should be able to run any software. For example, from a light software like internet browser to a specific and number crunching application like MATLAB. So they should be able to run all these. So what are the user benefits? Low time to market and NRE costs. What can be the meaning of this? Low time to market, right? Why low time to market? Because it is already produced and available for you. You just buy a motherboard, you plug in the microprocessor, and then you're ready to go. So low time to market and low NRE cost as you are concerned. I do not mean to say, or it does not mean to say that it is a low NRE cost for the manufacturer of the microprocessor, right? The manufacturer of the microprocessor would have spent lots of hours and lots of time in research and development for that. But we as users are better off because we can just purchase the microprocessor and use it. High flexibility, or I would say highest flexibility, because it is programmable. So since it is programmable, highest flexibility. You just change the program and there you are in a different application. There are other processors, right? There are lots of processors in the market. So after that we can take a look at the single purpose processors. As I discussed before, it is the extreme. Single purpose processor is designed by converting the algorithm into a processor technology. So single purpose processors are designed for only your algorithm. So you can see how simple is the controller section, consisting only of the control logic and the state register. It's a very bare bones sort of FSM that is there. And when we look at the data path is also very simple. It consists of two registers, index, total, and a functional unit plus, and simple data memory. So it is also known as coprocessor, accelerator, or peripheral. So it is a digital circuit designed to execute exactly one program. That is our algorithm, nothing else. So what is the advantage? Of course, since it is very focused and it is designed just for our algorithm, it contains only the components needed to execute a single program, which is our algorithm, and does not include any program memory. So of course it's fast because it is very compact and less number of things are there, highly optimized. Low power, of course, because it has got very less number of functional units and registers. Small size, yes, because the total number of blocks that are put on silicon is very less. So we have a very small size of the single purpose processor. Now look at what is called as a application specific processors. Application specific processors are also called ASIPs, application specific instruction set processors. So both terms are equivalent. So they are programmable processors optimized for a particular class of applications having common characteristics. Like this diagram that can be seen, and this diagram is very similar to the diagram of the general purpose processor, as we can see. So application specific processors are quite similar to general purpose processors, but they have got certain distinguishing characteristics. Like I mentioned before, there's the custom ALU designed to carry out certain specific operations very fast, for example multiply and accumulate instructions. So it's basically a compromise between general purpose and single purpose processor. So the performance of an application specific processor would be better than general purpose processor for a specific task. What's the meaning of that? For example, if you have a DSP, it would perform DSP better than a general purpose processor. But of course it would be slower, more power consuming, more bigger size than a single purpose processor, because single purpose processor is the ultimate in design performance. So what is the features? It has got program memory, it has got an optimized data path, because the optimized data path is optimized for certain application for which the ASIP is designed, and for that matter it has got special functional units. So what are the benefits of ASIPs? They have got some flexibility, good performance, size and power. After discussing the three processor technologies, single purpose processors, application specific processors, and general purpose processors, now we look at the discussion about the IC technology that can be selected to make a certain embedded system. So what is IC technology? The manner in which a digital gate level implementation is mapped into an IC. So whenever we do a digital logic based design, all embedded systems would be modeled using DLD techniques, digital logic design techniques, and we have something final that is called something as a net list, right? And this net list can be mapped or can be converted to any IC technology that we select, right? So what is the IC technologies we can use? We can use IC integrated circuit. IC is called as integrated circuit or chip. And what is the difference between the different IC technologies? IC technologies differ in their customization to a design. The general rule is that the higher the customization, more is the cost of the technology and more is the NRE of the technology. So lesser customization means lesser NRE for that particular matter, and of course less cost for small volume applications. So ICs may consist of numerous layers, right? Perhaps 10 or more, and this is basically the structure of the IC that is shown. For example, this is basically an FET that has been modeled in a IC manner, integrated circuit. So what are the three types of IC technologies? This we have the full custom / VLSI, semi-custom ASIC, and PLD, programmable logic device. So if we consider the customizability is like that. VLSI is most customizable and PLD is the least customizable. And if we compare it by the cost, VLSI is the most costly and PLD is the least costly for small volume applications, and ASIC comes in the middle, right, in terms of customizability and cost. So what do we mean by full custom VLSI? All layers are optimized for an embedded system's particular digital implementation. So VLSI is the most lowest level design that we can make. So we are responsible for even placing the transistors, for setting the size of the transistors based on power requirements, of course, and we are connecting or routing the wires between these transistors and wires. So what are the benefits? Excellent performance and small size and low power. So VLSI is the best you can do in order to make an embedded system. What is the drawback? Drawback is an extremely high NRE cost. And since you are designing everything yourselves, a very long time to market. So one of the things that when Intel manufactures microprocessors, to get these benefits, Intel uses VLSI. But of course this VLSI technology is used for large scale or mass production of microprocessors by Intel, so that this cost is divided by the number of processors. So we have a certain VLSI cost, and we divide it by the number of units. Sorry. So the higher the number of units, the lesser this factor would be, and this would be the lesser contribution in the cost of a single microprocessor that is produced by Intel. Now we can look at semi-custom, and in semi-custom basically the lower layers are fully or partially built. So we are not making or sizing the transistors. It might mean that some of these layers are already built, the transistors are already built, the sizes of the transistors are already built, and so on. So we won't be working at this low level, we would be working at a little higher level. So what is the designers left with? designers adapt with routing of wires and maybe placing some blocks. Some blocks may be placed and routing can be performed. And as you can see, since we have less work to do in semi-custom or ASIC, we have less NRE cost and less time to market as compared to VLSI. And the benefit is generally good performance, good size, and this low NRE cost of about 10k to 100k. It might vary according to today's manufacturing things. So what is the application specific IC? ASIC is basically cells of certain functionality, and these cells are produced in the these cells can be produced in the IC in the semi-custom manner. What are the drawbacks? It still requires time to develop, weeks or months to develop. So NRE cost is less than VLSI, no doubt, but NRE cost is there. Now we come to the PLD, programmable logic device, which is one of my favorites as well. In this, all layers already exist, so you can't do any customization in the structure of the IC. It is already built. So what do we do then? So we can connect the ICs with the connection between the ICs can either be created or destroyed to implement desired functionality. The excellent examples are PALs and GALs. Low end examples, PALs, GALs, right? All the arrays of gates is already built, and we make connections between the gates in order to carry out functionality. A bigger example and more powerful example is an FPGA, like I've been discussing before, in which we can implement logic circuits as well as full soft core microprocessors. So what are the benefits? Low NRE costs, because you don't have to develop anything at the IC level. There's no NRE involved in that. So you just buy the IC and then you use it, because we have an almost instant IC availability. So what are the drawbacks? It is bigger, expensive, power hungry and slower, because everything is already made. But I told you to manufacture your embedded system in smaller quantities, or in other words, to manufacture your embedded system in smaller quantities and less time, and in fact prototyping. If you want to test your design, so PLDs, for example, FPGAs are excellent technologies for prototyping or testing your digital design. You can reprogram until you get the functionality correct. Now we can look at the design technology, and by design technology we mean the manner in which we convert our concept of desired system functionality into an implementation. So we have to convert our functionality into an implementation. So this is basically the flow that is used, right? So we'll first have the system specification, and at this stage we can have the compilation synthesis, we can have system synthesis, hardware software synthesis, operating system support, and we can have test verification at this level, which is model simulation, checkers, etc. So after this stage we move on to the behavioral specification, and the tools that are available is basically behavior synthesis, and the libraries at this stage would be called cores, and to test at this level we need the hardware software co-simulators. So if our design is verified at this stage, we can move to the register transfer specification, and the tools that are used here are register transfer synthesis, and the libraries that we have at this stage is register transfer components. And to test this RT, register transfer, or RTL, register transfer level specification, we can use HDL simulators. So after this simulation is correct, we can now move to the logic specification, and the tool here can be the logic synthesis tools. And what would be the libraries that would be used? Gate cells. And how can test and verification be performed at this stage? By using the gate simulators. So once all these stages are satisfied, we move to the final implementation, right? So this compilation synthesis automates exploration and insertion of implementation details. So every layer can be used as a model for the lower layer as it is designed. So now the famous point about embedded system designers that I have been referring to is basically the term co-design, right? And by co-design we mean that embedded system designers have to be both hardware as well as software experts for designing embedded systems, because the various trade-offs and the various decisions that these designers would make would depend on definitely if they have the great knowledge about hardware and software. Things that can be done economically using hardware would be implemented by hardware, and things that can be done economically using software would be done using software. But again, the decision, you can make a decision only when you know the strengths and weaknesses of hardware and software. So basically we are involved with hardware software co-design in the example of an embedded system design, and this is basically the term co-design. So there were separate ladders previously, but now of course everything is combined. So the designer must partition the different components of an embedded system. So this is the punchline: the choice of hardware versus software for particular function is simply a trade-off among various design metrics like performance, power, size, NRE cost, and especially flexibility. The punchline is there is no fundamental difference between what hardware or software can implement. So in other words, whatever that can be implemented in software can be implemented more efficiently in hardware. So now look at independence of processor and IC technologies. This is a very important point that is misunderstood by many embedded system designers. So these are the design implementation or technologies, IC technologies that are shown, and these are the processor technologies that are shown. The idea is that this layer is different from or independent of this layer. So general purpose processor can be implemented on a PLD or semi-custom or full custom, and for that matter single purpose processor can be implemented using VLSI. It can be implemented using ASIC, and it can be implemented using a PLD. So what is basically at the PLD level? Flexibility, maintainability, low NRE cost, low time to market, and low time to prototype, and the cost is low in low volume applications. Okay, and the same is true for full custom, right? Power efficiency, performance, size, and the cost would be low for high volume applications. And this ASIC at the semi-custom is basically lying in the middle. Remember that example that we did. This graph, right? So over here technology A was basically the PLD, like I told before, because it was less for less number of units, and this triangle ones were the ASIC technology, and the cross was technology C. And as we can see, technology C is basically our VLSI, technology B is ASIC, and technology A is PLD. So when we have very high volume, large number of embedded systems to be manufactured, technology C definitely has a lowest total cost. And if we have low volumes, PLD is feasible. And if we have moderate volume of our embedded system, the value is greater than N1 but is less than equal to N2, then we have basically what? The ASIC or the semi-custom. So these two layers are independent of one another. Now we look at design productivity gap. Basically what it shows us is basically two things that have been shown: the IC capacity and the productivity of the designer.